let's broaden our understanding on PCB width. First, let's understand why trace width is so important. Imagine we have a tank full of water and pipes with 3 different sizes: small, medium, and large. When high pressure is exerted from the water, the smaller pipe will break down. Similarly, smaller trace width will adversely affect the PCB, eventually burning it out. On the other hand, using a larger pipe will be an overkill. Space wastage. Cost implications are some of the issues. From this analogy, I hope you got why trace width is important. In this video, I will be explaining which factors affect the trace width and major considerations related to them according to IPC 2221 standard. IPC, Institute of Printed Circuits, have published rules and regulations for the safety and better performance of the boards. Our main concern today falls under 6.2 conductive material requirements. I will be going through the equation and the graphical approach for the better understanding. Let's discuss the factors affecting the trace width. 1. Current capacity. 2. Trace thickness or the copper weight. 3. Temperature rise. Let's straight away move on to the equation and see how these factors affect on trace width. I equals K multiplied by delta T to the power 0.44 multiplied by A to the power 0.75. I denotes the current going through the trace in amperes. This depends on the electronic equipment you are using. For example, 1.7 amperes for NEMA 17 motor. Letter K is a constant. K equals 0.048 for outer layers and 0.024 for inner layers. Delta T represents the temperature rise in Celsius. General purpose PCB usually use 10 to 20 degrees Celsius, although aerospace industries and medical industries go below 5 degrees Celsius. Finally, A, which represents cross-sectional area. In square mils, mils is for 1/1000th of an inch. Cross-sectional area can be written as a product of trace thickness and trace width. So, by substituting values for I, K, delta T, and trace height, we can find the correct values for the trace width. Now, let's take a look at the graphs provided by the IPC 2221. For K equals 0.048, they have provided this graph. First, we have to choose the proper temperature rise, which is delta T. According to that, we can choose the correct curve. Then, we have to find the current that will be consumed and draw a horizontal line. Then we have to draw another vertical line, starting from the intersection of the previous 2 lines. After getting the value for A, substituting trace thickness into it will give us the trace width. Similarly, this is the curve for 0.024. This is a lot of work, but not to worry, there are multiple ways of calculating these using online tools. This is the online tool that I use, VG Key. Just type PCB width calculators in Google, and you will find plenty of calculators. Here I will use current equals 3 amperes, thickness as 1 ounces square foot. This is the common standard to express thickness or copper weight, and finally temperature rise T as 15. As you can observe, I have found the trace width as 2.78 millimeters. You can use mils or millimeters, any unit you prefer. Now you might wonder why I did not use trace length and ambient temperature. I will talk about those in the next section. Final, and the most important section, major considerations, choosing the trace width. 1. Trace length. 2. Signal integrity. 3. Spacings. 4. Environmental impact. Trace length. Trace length is as important as trace width. From the formula of resistance, we can observe that when the length increases, the resistance also increases. And also we can observe that when area increases, the resistance decreases. Since area is a product of width and thickness, when width increases, the resistance decreases. So, when routing power lines and signal lines, we need to understand the resistance generated, power loss, and voltage drops that have occurred. Understanding these concepts will enhance the performance of your PCB. Moving to the next, signal integrity. Signal integrity refers to maintaining the quality of electrical signals as they travel through traces on a PCB. It ensures signals are transmitted and received accurately without distortion, noise, or delay. Think of it like delivering a package. If the path is bumpy or crowded, the package may be delayed, damaged, or lost. Few of the possible causes include reflections, crosstalk, noise, timing issues, and ground bounce. By controlling the trace width, we have the ability to get rid of most of these causes. For example, impedance matching using differential lines, applying wider ground traces, or maybe a whole plane, and adding delay lines will help to mitigate causes. Spacing. This is one of the biggest and common issues. Spacings, which implies the capability of the manufacturer. For example, JLC PCB have provided us their manufacturing capabilities, such as specifications, drilling, traces, solder mask, legend, and outline. Even though your PCB has the best performance, with perfect signal integrity, it does not matter if the manufacturer can't build it. Therefore, we must respect the clearance rules and follow manufacturer's capabilities. Finally, our last topic for the day, environmental impact. Let's break this into two major parts, ambient temperature and airflow impact. The ambient temperature is the temperature of the environment where the PCB operates. Higher ambient temperatures reduce the trace's ability to dissipate heat, which can lead to overheating. For example, in a 25 degrees Celsius environment, a trace can safely carry more current than in a 60 degrees Celsius environment. Airflow impact can be further divided into two parts, static and dynamic. Static cooling relies on the natural dissipation of heat, less effective in enclosed or poorly ventilated spaces. Dynamic cooling, for example with fans, enhances heat dissipation and allows narrower traces for the same current. I hope that I have helped you to broaden your knowledge under trace width. If you have any question, please put in the comment section. Thank you.